Okay, so in the last video we started finding the principal axes for a rigid body, and we found that we could certainly do it by finding the eigenvectors and eigenvectors of the moment of inertia matrix. But as you can also get a sense, that can get kind of tedious. It's often the case that we can use symmetry to find some shortcuts. So what I've drawn here is I'm imagining that I have a cube that is being rotated about its opposite corners. So I've just marked my XYZ origin here O, and then the opposite corner I labeled A. And if you look at this line OA, which I've labeled X1 as well, you can see that there's a lot of symmetry about this line, and I'm going to argue that this is one of our principal axes, which is why I've decreed that that's our X1. For instance here, if I could pick any x2 or x3 as long as they're perpendicular to each other and to x1. And it's clear that if I look at any triplet of points that are symmetric about A, for instance, this triplet will do, the 2, 3 product of inertia is equals sum over my masses, m alpha, x alpha 2, x alpha 3. It will always work out that this sum will add up to 0 is for this choice of x1. So we can conclude then that I23 is equal to 0. Now let's go ahead and look at, say, the 1, 3 product of inertia. That would be equal minus sum over alpha m alpha x alpha 1 x alpha 3. Now here, the x alpha 1s are always positive. With the 2, 3 here, we took advantage of the fact that you had both positive and negative contributions. So for instance, positive, negative, you get some cancel there. Here with the 1, 3, it's going to be the case that the x alpha 1s are always positive, but even here, if I say go ahead and look at strategically chosen pairs of points, like say, let me go back to orange there, like say this point here and this point here that I've circled. If I go ahead and look at those pairs of points, you'll get that you have opposite values of x3. They'd have to be negative with each other, again, regardless of how we orient our x2 and x3. So they would have to cancel. So we can conclude that I13 is 0, and by the same token, we can also include that I23 would be equal to 0 for this choice of principal axis. So if you see symmetry, it's a really good chance that you've got yourself a principal axis. That's probably a less obvious case, but we could certainly look at a case that's more obvious. Let's look, say, at our cube again. Yeah, I can draw a cube. There we go. And look at our cube again. And we can go ahead and pick the center of mass of the cube, like so. And if we want to rotate about axes that are going through the center of mass, I think it's really clear that, say, this choice here for x1, this choice here for x2, and this choice here for x3 are going to be our winners. Clearly here with, let me relabel my x2 correctly. Whoops. There, much better. Alright, so I'm clearly with this choice of x1, you've got matching pairs of points above and below, so that's going to make my x2, 3 vanish. Right and left here will make my x1, 3 vanish with this choice of x2, and right and left about x3 will clearly make my I1, 2 product of inertia vanish. And so just from the symmetry of the cube itself, we picked out the principal axes. Okay. So how about, so a lot of times, like in this first case here, where I wanted to spin it about a corner, we could pick out this, from symmetry, we could pick out the OA as our axis there. How about if you got something that's a little less obvious, like, say, following the book's example, a ping pong paddle, like so. We'll put the origin here. It's abundantly clear that that's got to be a principal axis. It's less clear where we should be pointing our x1 and x2. Another example that we could look at is, say, a fan blade, and I'm going to tell you this is a fan blade because I can't draw one that good. So we'll go ahead and put it about the symmetry center of the fan blade. And again, it's kind of screamingly obvious that going right down the fan blade is one of our principal axes. Now, if I just kind of do the obvious thing here and say that this is y, here, let me draw that dashed. This is y, and that's x, like so. It's not entirely obvious to me, anyway, where the x2 and x1 axes should point. The only thing I know for sure is that they need to be mutually perpendicular to each other and to x3. Well, if my fan blade is rotating, I can at least go ahead and pick out my, so here I picked out an x and y axis I understand that are convenient. And I'm going to try and find my x1. Let's say it's here, and my x2, let's say it's there, because the problem is, of course, with the fan blade, you've got a twist in the fan blade, which I can't draw very well. So here's my x1. There's my x2. All right, so with that, my moment of inertia tensor, since I know that x3/z is a principal axis, the products of inertia, the 1, 3 and 2, 3 products of inertia have to be 0. So my matrix has to look something like this. And I'm just I3, 3. And since we already know this is a principal axis, we can go ahead and relabel that just I3 down there. And we also know from symmetry that I1, 2 and I2, 1 have to be equal. So I'm going to go ahead and call them both I1, 2. All right. Now, let's go ahead and say that x1 is a principal axis. Now, we don't know where it is yet, but let's say it is. The hallmark of being a principal axis is that if my angular velocity vector omega lies along it, my angular momentum vector L also has to lie along it. So that's what we're going to do. We're going to demand that it lie along there. So I can go ahead and say that my angular momentum L, that has to be equal to I dot omega, and that will be equal to I11, I12, 0, I12, I22, 0, 0, 0, I3 times the coordinates of my omega, but there's no omega 3 component or omega z. So omega x, omega y, and 0, like that. Now, like I said, we're choosing to point, this is true in general, but I'm choosing to point my omega along the x1 axis, which I don't know yet. But the one thing I do know is that that's an eigenvector, by definition. That's an eigenvector of my moment of inertia tensor. So I can replace the moment of inertia by the eigenvalue, which we'll just call I1. And so I can say that L is equal to I1 times my omega x, omega y, and 0. Okay, so with that, we can go ahead and equate our components of L to figure that out. So first I'll multiply this through. That's going to give me I11 omega x plus I12 omega y equals, then equating from here, that has to be equal to I1 omega x. And then for this y component here, that's going to give me I12 omega x plus I22 omega y. And that also has to be equal to I1 omega y. Now, the one thing we do know is this angle that we're pitched off of the x-axis. Let's call that angle there theta. We know that the tangent of theta has to be equal to omega y over omega x. So what I'm going to do is I'm going to take this system of equations here, and I'm going to divide it through by my omega x. Alright, so if I do that, that gives me the system I11 plus I2, I12, and now I'll have an omega y over omega x, so it's tan theta. That's equal I1, dividing that through by omega x. And similarly, I12 plus I22 tan theta equals, now this is an omega y, so I pick up an I1 tan theta from there. All right. Well, conveniently, I have I1 in terms of my unknowns here, so I can certainly plug it in down there to get my theta. So that's going to give me I12 plus I22 tan theta equals I11 times tan theta plus I12. Now I got two powers of tan theta, one from here, one from there. So tan squared theta. All right. So I can rearrange. I'll have I22 minus I11 tan theta equals I12 times tan squared theta minus 1. All right. So if I divide through both sides by the things that are in parentheses and multiply by 2 just because I feel like it, I'll have 2 tan theta over tan squared theta minus 1 is equal to 2 I12 over I22 minus I11. And the reason I felt like that is that is an identity. This is tan 2 theta. So there you go. If it's screamingly obvious where your x3 axis has to point, just pick an x and y that you understand, and then this will give you the angle off of x and y that your principal axes have to point. Theta. Cool. In the next video, we will go ahead and take up Euler's equations of motion for a rigid body.